We will now solve problem 3 given in the spring exam of 2017. So first we have a triangle where we have to work with sides and angles, and then we have a trigonometric function where we are to work with amplitude, period and stuff. So let's start with the A. Here we are to decide the sides A and C when we're given the side B and the angle B. So we know this angle B and the side B. And if we start with the A, we need to figure out which equation to use. And here it would be tangent. The tangent would be the opposite side divided by the adjacent side. And since we want A, we will multiply with A and divide by tangent B. So please distinguish between the side B and the angle B. Side B is 3 and the angle B is 60 degrees. The exact value here for tangent is the square root of 3. So this would be square root of 3, which is 1.73 approximately. So that was the side A. If we were to do the side C also, we see that now we need to use sinus, and that would be the opposite side divided by the longest side. We want side C, so we multiply by C and divide by sinus B. Again, B is 3 and sinus the angle would be 60 degrees, and the exact value is a half square root of 3, which would be square root of 3 over 2. No, not square root of 3 over 2, sorry. We need to multiply with 2, so we get 2 square root of 3. That would be 3.46 approximately. That was A. B. Now we are to determine the angle A and the angle B when we know that A is equals 3B instead of what we had before. Okay, so if we start out with A, the angle A, side A and side B, we see that now we need to use tangent. And that would be the opposite side divided by the adjacent sides. That would be 3B over B, which would be 3. So A would be the tangent inverse of 3. Note also that two things. You need to have your calculator set on degrees because we're working on degrees. And secondly, the notation. This is also known as arctan or atan. This is on the most calculators, but you will also occasionally run into this. But just put it into your calculator, and that would give you approximately 71.6 degrees. You also want to know the angle B. And again, we need to use tangent. And that would be the opposite side, which is now B, divided by the adjacent side. So we have B over 3B, which is 1/3. And if you check this, take the inverse of that, you would get approximately 18.4 degrees. Note also that you're able to check these, because 71.6 degrees plus 18.4 degrees, that would be 90 degrees, which is what we were supposed to, because if this angle plus this angle plus this angle is 180, we're okay. And in the same, so you could also use the angle A to find angle B by simply subtracting 90. Here also you can check, because A squared plus B squared should be C squared according to Pythagoras. That's a good way to check. But let's move on to C. Here we're giving a trigonometric function of describing the water level in meters relative to mean level. So the waves would go up and down. Because t is then the time in seconds. A positive value means that we're above the mean value, and a negative, of course, lower. So now first we want to decide on the amplitude. The amplitude is what we have here. So the amplitude would be 2. Because cosine fluctuates between -1 and 1. And if we multiply that with 2, we get from -2 to 2. So that was the amplitude. I often put a line underneath when I've done it, because I need to make sure that I have everything. And now we're going to find the period and the frequency. The general form is like this, where we have the amplitude, and here we have the angular frequency. So our angular frequency, that would be omega equal to 0.73. So our frequency actually now we're into radians per second, but our frequency would be 2 pi omega divided by 2 pi. So we have 0.73 radians per second divided by 2p radians. Sometimes you don't really need the units here, but you could either use radians per second or simply 1 per second. And if you do that, you'll get approximately 0.116 Hertz. Hertz is defined by 1 per second. So that would be our frequency, and our period, that's simply how long is one period, and we can measure one period from top to top, or from bottom to bottom, or the same phase. And that would be 1 over frequency. So that in this case would be 1 over 0.116 Hertz, which would be approximately 8.6 seconds. So during 1 second, we managed to have 0.116 parts of a period, and one period would be 8.6 seconds. Now we have the period and the frequency, and we're done with C. D. For 0 less than t less than the period, where t is the period, Find the time interval when the water level is higher than 1 meter above mean level. So let's just make a sketch here. This doesn't have to be accurate at all, but just so we have something to work on. So this would be our period, and this would be our graph. Our amplitude would be 2, so that would be the maximum value, and our minimum would be 0.2. Okay, so now we have a graph that is we can use as a simple sketch. Find the time interval when the water level is higher than 1 meter. So you want to know when it's higher than 1 meter. So we see that this is we need to find this value here and this value here, because our result would be this interval and this one. So what we need to do is to solve the equation where f of t equals 1. Not f of t equals, sorry, we need to solve equals 1. So we need to solve 2.0 cosine 0.73t equals 1. So when is cosine 0.73t equals 1 divided by 2? 0.5. Well, our primary solution would be when we simply take the cosine, inverse cosine. And the inverse cosine would be something like 1.047. So we have t equal to 1.047 divided by 0.73 approximately. So that would be 1.43. So here we have t, which was 8 point something, 8.6. So it doesn't sound too bad that this would be 1.43. Here we would have 4.3, half of the period. So yeah, this sounds good. The secondary solution this is where we are to find what we have here. And there's several ways to do that. The simplest way is simply to take the length here and then realize that that has to be equal to the length here. So we subtract 1.43, our primary solution, from the period. So our secondary solution would be our period minus, we could put a t1 and a t2 here. So then we can take our first, our primary solution as t1. And that would be 8.6 minus the 1.43 thing. Here we should have had one decimal more. I still have that in my calculator. So I get approximately 7.17. And that doesn't sound too bad either. If we were to find remaining solution, we're not supposed to do that, but let's say we were. Then the t would be our primary one plus our period, as many periods as we want. So if we start out like this, here we have our t. So this would be a first, a primary, a secondary, and if we add one period, we will get the third. Add one period to the secondary, we get a third. Here we have 2t. Here we have our primary plus 2 periods. So the n has to be an integer, 1, 2, 3, 4. And this one would be 7.17, a secondary solution, plus any number of periods afterwards. We're not supposed to do that because we need to find only solutions only in the interval where t is between 0 and t. But we wanted to know where it was above mean water level, 1 meter above. We only found the solutions where it is equal to. So above above 1 meter, that would be 0 to our first one, and our second one up to our period. So we have two intervals, namely the two are marked with red in this graph. Okay, E. Find an expression for how fast the water level is changing up and down due to the waves. The rate of change is simply the derivative. So if we have f of t equal to the expression given, we start out with that 2.0 cosine 0.73t. We then get the derivative. We need to find the derivative of cosine, which is minus sinus. We need to keep what's inside the parentheses because that's trapped in there. And then we need to find the derivative of what's inside the parentheses and use the chain rule. So we have applied the chain rule here. So that would give us f derivative t equals to minus 1.46 sinus 0.73t. So that would be an expression for how fast the water level is changing. For example, if t equals 0, we get something with sinus 0, which is 0. Not surprising, because we have a cosine here, and that one starts at the top and then go down and then up again. So here we have a maximum point where the derivative is supposed to be 0. And the same if we go to t, you'll also see that if you insert that, you will also get 0, because then we are a new maximum. And a half t would give a minimum, so that one would also become 0. But if you go to 1/4 of a t, you will have the maximum change. Yeah. But this is not required at all, just to make you understand what the expression shows.